Ethernet auto-negotiation is used extensively in most networks. However, when you're first learning about it, it can be pretty confusing. In this video, we're going to slow down and make sure you understand the ins and outs of Ethernet auto-negotiation. So as usual, here's the context. I follow the outlines of the books. So this content mirrors some you'll find in the Volume 1 Cert Guide, Part 2 in Chapter 7. Now that chapter has two major sections, but the first section is longer than I want to put the equivalent material in one video. So this video is about half of the content in that first major section, specifically about auto-negotiation. What specifically? Well, I'll talk about IEEE auto-negotiation in the first bit, about how it's supposed to work. Then I'm going to give you a brief demo of seeing that work on real gear. By the way, Packet Tracer has some issues with mimicking real-life auto-negotiation on switches, so I'm going to show you real switches in the demo. And then the thing that tends to confuse people is this topic of what happens when one link partner doesn't use auto-negotiation and the other one does. Cisco says, don't do that, but it can happen, so you need to be ready for that and you need to understand it. So that's where we're headed. All right, so what's the extra at the end this time? Well, there are some difficulties in recreating the problem that happens with auto-negotiation called a duplex mismatch. So I'll coach you through how to accomplish that in lab. It's trickier than you might think. As usual, I'll coach you then about how to use the book section in comparison to this video. It's a little tricky this time because I'm doing about half of the section. And then for those of you that do or don't have the book, I will talk to you about a review activity. This time it's one review activity at the end of the video. So watch for that as well. Let's get into it. So let's talk about IEEE auto-negotiation when it's working correctly on both endpoints. I'm going to start with a bit of an analogy. Imagine a couple sitting at dinner and they're talking and they're adults. So their sound waves, if you were to graph the sound waves, it might have a certain amplitude and frequency based on the sound waves. They're talking back and forth. And then later, another time, they're at dinner and they brought their kids. And so they're the little folks, they're sitting there talking. And maybe their sound waves, if we graph them, have a little bit different characteristics. Maybe the amplitude and the frequency is a little different because they're kids. They've got different voices, right? So if we look at a graph of what a sound wave or electrical wave looks like, they'll have different waves, different frequency, different amplitude, and different phase. And these things can be changed by our voices to make words, and changed as electrical signals on Ethernet to imply a 1 or a 0 in order to communicate. So now if I take that analogy of different people having different conversations with different sounding voices, and then I think, all right, well, what could happen on an Ethernet link? Well, it turns out that there are different frequencies used to send data that's overhead data to support IEEE auto-negotiation. So imagine this switch and a PC that's connected to it, and they're going to use auto-negotiation, but they're also going to send data frames, and most of what they do is sending data frames. So let's talk about those for a moment. So if I talk about the quote data encoding, that is, I'm encoding frames that are Ethernet frames that we talk about so much for CCNA. There are details about what the electrical signal looks like, about the amplitude and the phase and the frequency. And that changes, and changing that signal implies 1s and 0s that make up the bits in the frame. Now, each speed, each part of the 802.3 standard that defines a new physical layer part of the standard has a different encoding. Right? So each one, like 10 or 100 or 1,000 megabits per second, it's different details of what this waveform looks like. Then in addition to that, the auto-negotiation process has a completely different signal that it sends, and it's based on a term called fast link pulses that grew up for other purposes, but over time these have become a way for Ethernet to have a way to send some data for overhead purposes, like saying, here are the speeds I support and here are the duplexes I support on the link for the purposes of auto-negotiations. And those are not the same electrical characteristics and same signal as the encoded frames that we use to send Ethernet frames at whatever speed gets negotiated. They are separate. So it's just some overhead data in these FLPs. So what's going on when auto negotiation happens? Well, when the link first comes up, both endpoints will send these FLPs, assuming they're both using auto negotiation for a bit. So they're sending these things, and they'll say what the endpoint supports. Like switch 1 announces I can support 10, 100, and 1000 megabits. That is, it's a 10, 100, 1000 port. And that it supports both duplex settings. Then PC2 may announce the same thing. He supports all three, both duplexes, and we've highlighted the best, right? You got 3 speeds. We want the fastest speed. We've got 2 duplexes. Full duplex is way better than half duplex. So if both of them declare these facts, they're going to agree, hey, let's use the best speed and the best duplex, and that's what they'll use. And that's what auto negotiation is supposed to do, and that's indeed what happens. So when does it happen? Let's talk about process for a moment. Say the link is down. Say one of the devices is powered off. The other device is trying to send these FLPs, but it can't even make an electrical circuit happen. Then when both devices are powered up and the electrical circuit can start to work, they start with FLPs. They don't start with data frames. So these FLPs flow, both endpoints hear from each other, they figure out what both endpoints support, and then once they think, I know what speed I'm using, I know what duplex I'm using, they can start sending these data frames. Say, for instance, they chose full duplex at 1000 megabits per second. They might start sending the signal and say it's encoded per the 1000 megabit per second or 1 gigabit per second standard. Great, we're sending data frames. But what about these FLPs over here, right? Well, it turns out those stop, right? The endpoints don't have any need for it. So this auto negotiation process happens at link initialization. They negotiate, they pick a speed and a duplex, and they use it, FLP stop. So let me take you through a brief demo, and I'm going to use switch SW1 here from my lab. I'm going to use the show interfaces status command and point out a single interface here. And let me just make a few comments. I'm not teaching you the command so much here, but I want to make a couple of points. This command output shows the speed and duplex that's being used on a link if the link is in an up or connected state. And here it says A full and A1000. When the values are preceded by an A dash, it means these are created because of auto negotiation, right? So it auto negotiated to use full duplex and a speed of 1000 in this case. So I'm going to take you through a few scenarios here where I'm going to change a setting that redrives the auto negotiation process. I'm going to get into config mode and get into interface mode. And if I just set speed to 100, here's what's going to happen. It resets the speed, but the switch knows, hey, I need to renegotiate with the other side because I've changed something that might affect the speed. So you see that the link went down, it came back up, and unseen by us, all these fast link pulses happened. So where did we land on our speed and duplex? Well, by the way, that do command says do a show command from inside of config mode. And if we look here, we see that the duplex is full duplex per auto negotiation, but speed is 100, not prefaced with the A dash because the speed was per a configuration command rather than being per a auto negotiation process. But it redrove the process. So if we did something like, hey, let's change the speed to 1000. Hey, the speed might have changed. We need to renegotiate. Auto negotiation is on the interface, and it's going to go through FLPs because the link went down and back up. Now that it's back up, I just up arrow twice to retrieve that command, and I see that we're still using auto negotiated full duplex. Now the speed is 1000 because I just configured it. And then just one more. What if I said speed auto? What does that do? Well, on this interface it says use auto negotiation to pick your speed. And we're going to get the link down messages and then the link up messages. There we go. And if we up arrow twice and retrieve that show command, now we're back to the case where we auto-negotiated a speed of 1,000. And that's what you'll get if you have the books and look at the rest of that section, or one day when I create a video on the second half of this first section, I'll work you through all these commands and talk through that more. But most importantly, for auto-negotiation, what's happening is every time the link goes down and comes back up, what happens when the link comes up? FLPs, new negotiation happen, new choice for duplex and speed. That covers the case with both endpoints participating and using auto-negotiation. A lot of the confusion happens, though, when one endpoint chooses not to. Now, throughout Cisco documentation, Cisco says, don't do that. Configure so that both endpoints use auto-negotiation, and if you must do something that deviates from that, make sure that neither tries to use it. So either use it on both sides or don't use it at all on a particular link. But let's talk about the case where you stupidly use it on one end and not on the other, because it can introduce problems. So let's just say we somehow managed to disable auto-negotiation on one end. We're going to disable it on PC2 in this example. So switch 1 is using it, so it sends FLPs when the link comes up. But what about PC2 down here that's not attempting to use auto-negotiation? Well, it's got to have some configuration that tells it what speed to use. And say it's got a speed that's, I think I do 100 in this case, yeah, and it starts sending data frames based on the encoding definition for that speed. So no FLPs at all in that case. All right, so those FLPs coming down from the switch, they might say some things like I can do all the speeds, I can do half or full duplex, but PC2 ignores those and just starts sending these frames up to switch 1. Now the IEEE auto-negotiation spec accommodates that. The formal term is parallel detection. I added that to the books in the edition 2 books that came out in 2024. I don't know that the term itself matters so much for CCNA, but I decided to go a little deeper with auto-negotiation in this edition. So here's what that means. It means, hey, I'm going to send FLPs if I'm trying to do negotiation, auto-negotiation, but if the other guy doesn't, in parallel, I'm going to do other things so I can make the link work. All right, so what's switch 1 that's attempting auto-negotiation trying to do here? Well, remember PC2 is not using auto-negotiation. It's just sending data frames. Switch 1 is expecting FLPs but does not receive any. So parallel detection says, hey, I got to do something here. And the frame that's coming in is encoded per the spec for 100 megabits per second. And switch 1 can figure that out because the encoding for every speed is different. It's not like the encoding is the same with 10 and 100 and 1000. It just looks at the electrical signal and says, hey, they're sending frames at 100 meg. So what should switch 1 do if it knows the frames coming in are being sent with the 100 megabit per second encoding? It should use 100 megabits per second as the speed, right? That seems somewhat obvious. So it recognizes the incoming encoding and chooses the speed based on that. The problem comes in that it has to guess what duplex to use. It chooses the duplex per a table, and the table is set up based on the history of when these standards came out and what was common at the time. So if this parallel detection logic detects 10 or 100 megabits per second, then the endpoint that's attempting auto-negotiation, switch 1 in this case, that's having to make a guess at the duplex is going to pick half duplex. If it figures out the speed is 1 gigabits per second or faster, it's going to end up with full duplex. So in this case, PC2 was sending at 100 megabits per second, so the switch would pick half duplex. All right, so that's the logic with parallel detection, as it's called, the logic applied on the end that's attempting to use auto-negotiation. So let's just say we had a broader example. We've got this switch, and all its ports are 10, 100, 1000 ports as labeled here. And we don't have any configuration on the switches, so they're attempting auto-negotiation. Whereas we've managed to configure all 3 of the PCs to disable auto-negotiation, and the speed and duplex are preset. it is possible to make really dumb choices on the PCs and cause problems. All right, so that's why Cisco says don't do that. Just rely on auto negotiation. So I'm going to walk you through that. So the switch up there is going to be sending these FLPs, not getting any reply. It's going to notice PCA is sending frames at 10 megabits per second. The switch will choose to use 10 meg, and from this table, choose to run at half duplex. There's your logic. Or say PCB is sending frames in at 100 meg, not sending FLPs, but just sending data frames at 100 meg. Switch 1 says, hey, I can sense it's 100 megabit frames. I'll use 100 meg. I'm using half duplex because that's what the table over there tells me to do when I know the frame's coming in at 100 megabits per second. However, this third one, you can guess where I'm headed. Speed 1000 here, or 1 gigabit per second. The switch port ends up at 1000 to match, but then full duplex because the table says, hey, if you're using 1000, default to use full duplex. Now that might work well, or it might work poorly depending on the duplex settings down here on the PC. So if the configuration on the PCs stupidly configures the opposite duplex versus what you see on the upper part of the drawing, then it creates what we call a duplex mismatch, and that's bad. So in this example, just to spell it out, if we had happened to configure duplex full on PCA, that would not match the switch, duplex mismatch. Similarly, full on the bottom, the switch would have chosen half per this table. Again, duplex mismatch. And we do the opposite here. If we had configured duplex half down here and full at the top, again, duplex mismatch. So let me talk you through the issue with the duplex mismatch as we're wrapping up this issue. So I'm going to take PCA as an example. Remember, from that previous couple of pages of example, it was configured with full duplex, and the switch chose from that table of defaults to use half duplex. Here's what happens in that case, by the way. When choosing to use half duplex, it means that the link, the interface, uses logic that you might remember from earlier in your reading in videos called CCNA CD, Carrier Sense Multiple Access with Collision Detection. That's the fancy term for the logic that says that the device, before sending, has to listen, wait for silence, and then send, because it thinks there can be only one sender on the link at a time. So that's what the switch port does. Listens, hears silence, sends. Sends one frame that way, sends two frames that way, sends a third frame that way. But over there on PCA with full duplex disables CCNA CD. There's no need to even wonder if a frame is being sent on the link. You can send anytime. So A can send a frame anytime. Let's just say A sent a frame at nearly the exact same time, so the frames are going to pass on the cable. We've got this big orange swoosh in the middle, kind of like there's a collision. But is there a collision? With unshielded twisted pair cabling, there's not a collision on the wire. 10 and 100 meg, there are pairs for each direction. There's no collision on the cable. Here's what's happening. A thinks there's no collision, but switch 1 thinks there is, based on their logic and circuitry, not based on what's happening on the wire. So A is full duplex, says, I don't even have a concept of a collision on this interface. Whereas switch 1 says, a collision happens when I am sending a frame and I am receiving a frame at the same time, and they use some collision detection circuitry called a loopback circuit in order to test that. And the reaction of switch 1 is to back off, apply CCNA CD again, and resend the frame. So this fourth frame on the right, this one here, is a resend of the one just above. Yeah. So not only did we resend, in some cases, both frames, the original and the resend, will get through to the other side. In some cases, only one. and you'll end up having lots and lots of unnecessary retransmissions by the half duplex side. So it's kind of a mess to end up there. You don't want to end up there. Even worse, the link stays up, but you just have degraded performance. So you really want to avoid this. How to avoid it? Use auto negotiation and don't configure things like speed and duplex, which can open up the chances for turning off auto negotiation on one side and leaving it on the other. That's it for the core content. Let's talk about the wrap-up items here for a moment. As I mentioned, there's a long first section in the book chapter for Chapter 7. So here I'm just talking about auto negotiation. So in the auto negotiation section of that chapter, make sure you catch the topic about hubs and auto negotiation, which I didn't bother to get to here. Then the second half of that first section, one day I'll have a video on that here, assuming I cover all of the entirety of CCNA one day. But in the meantime, you want to make sure and check the second half of that first section in the chapter, which covers the configuration and verification of speed and duplex, as well as a topic called Auto MDIX. Then a review topic. We've got a terminology mind map. As usual, you could do it now. Better to wait a day or two. Even better to schedule it so you don't forget. I'm sure you can guess the seed term, right? Auto negotiation. And there's a video you can use to review it once you've done it for yourself. All right? So I promised you some suggestions about how to recreate a duplex mismatch in lab. So here's the traditional way. Connect two switches with an unshielded twisted pair cable. Configure speed and duplex. Traditionally, on older switches, that disabled auto negotiation on switch 1 in this case. By choosing full duplex and speed 100, it means switch 2, if left with all defaults. By the way, the defaults would be speed auto and duplex auto. With all defaults, it's using auto negotiation. It would sense the speed of 100 using parallel detection. It would pick a duplex of half, so switch 2 would end up with half duplex. Then you could do show commands and maybe generate traffic and see some collisions happening on the duplex side and see no collisions at all on the full duplex side because it has no concept of collisions. Now, why do I point this out to you? Well, it's fun to test that. The other is, it turns out I started getting cards and letters from people saying, hey, I did this on some real switches and that didn't happen. It wasn't a duplex mismatch. And it turns out that Cisco doesn't document the convention anywhere I can find, but I believe this is the case, that switch ports that support power over Ethernet, they don't turn off auto negotiation when you configure them as switch 1 is showing on the left. They keep it on, which is good because it avoids the duplex mismatch. So just be warned, if you go in lab and grab a couple of switches to try to do this, they happen to be switch ports that support PoE, you're going to have a tough time recreating this duplex mismatch scenario. So you might even be better off grabbing a couple of older switches to try to recreate it. So there's the extra help in lab. Thanks everyone for sticking around to the very end. If you could do something for me, give the video a like. If you do, give me a comment. Tell me what you did and didn't like. Give me suggestions about what to do next. And if you haven't already, click subscribe and click the bell so that you'll be notified when I put out new material. Hey, thanks for hanging out. Talk to you soon.